today we're going to be doing some Newton's second law, some kinematics, and squeeze in a bit of work and power calculations. So we're going to first start off with some multiple choice questions, and we're going to start with question 1.1. Question 1.1 asks us which one of the following quantities or following combinations consists of only scalar quantities. So let us go through our options sets. Well, that a velocity is not a scalar but a vector. Time, distance, and speed, well, all of those are scalar quantities. Remember that a vector is a quantity that has a magnitude and direction, while a scalar is just magnitude. So all of these are just magnitudes and no direction. What just happened, dog? I don't even know what happened, dog. Alright, moving on, we're going to be doing question 1.3. And for question 1.3, we have that a ball is projected vertically upwards from the ground and reaches its maximum height after a while. Ignore the effects of air friction. So this basically means we are looking at a vertical projection. So how will the acceleration and total mechanical energy of the ball at its maximum height compared to that immediately after it was projected? All right, so at its max height, we have a situation where the ball will be there and it'll be at max height, right, max h from the ground, and the velocity will actually be 0, right? But the mechanical energy will be equal to mgh, right, plus half mv squared. Now the velocity will be 0, yes, but because there's no air friction or losses in this case, the energy that the ball will have at being launched will the mechanical energy, right? It will have some velocity and some potential energy depending on where the ball is launched from, but all of this will be equal actually to the mechanical energy at that height max h, because of the conservation of energy. So we already know that it's going to be equal to. All right, now the acceleration, is it going to be equal to or smaller than? All right, so the acceleration acting on this thing is just the acceleration of gravity, which is 9.8. All right, at initial, so initially when it's launched. It's different after it has left the launch pad or whatever device. And at this max h, we also have this same acceleration. So this question will give us, or the answer to this question is A. Alright, moving on, we have question 1.4. It tells us that a car travels at a constant velocity even bolded everything for us. Along horizontal road, a constant frictional force acts on the car during its motion. Which one of the following statements are correct about the power dissipated by the engine of the car during the motion is correct? Alright, so we essentially need to find a relationship between power and force and velocity, and that is power is equals to force times velocity. Right, so what's correct about the power being dissipated? Well, since we have a constant velocity, right, we are going to need like we're not adding any energy or any more force into the system, otherwise we'll be accelerating, right? So that would mean that this F also needs to be constant, and if we have a constant force, a constant velocity, that means the power that we have should remain the same, right? Power that we have should remain the same. So the answer that we have is D. Alright, for question 1.5, we have that block X is placed on a horizontal table and is connected to block Y by a light inextensible string passing over a frictionless pulley as shown below. A constant frictional force acts on block X while it moves to the right. P, Q, and R are points on the table such that the distance from P to Q is equal to that from Q to R. Okay. When block X reaches point Q, the string is cut and block X continues to move towards R. Ignore the effect of air friction. So what happens? Alright. So we have this string, right, of a particular tension. I'm just going to draw the forces in the horizontal orientation, and we have some frictional force Fk. Alright, so this is situation number 1. Situation number 2, we're going to have a situation where the tension will be cut, and all that we're going to have is Fk, but we still have some movement to the right. Okay, that's what's happening here. Alright, now we need to consider the following statements. Statement 1, the work done by the frictional force acting on block X is greater when the block moves from point P to point Q than when the block moves from point Q to point R. Okay, and then both the momentum and kinetic energy of block X decrease when the block moves from point Q to point R. Now, reading this, I can tell you that this, to me, reads as more correct, because when we move to the right, we still have a velocity, right? But because we no longer have that force T pulling this block alongside, that means we're going to have a decreased V, right? So that means the kinetic energy, which has the term of V squared, half mv squared, will decrease. The momentum, which is mass times velocity, will also decrease, right? Yeah. And then for this work done scenario, well, essentially, we're moving the same distance and the force of friction isn't even increasing or decreasing. It's still the same. We didn't change the surface that we're on, right? So it cannot increase or decrease, right? So already this is not correct, especially since we know that P to Q and Q to R are the same distance. So it's not increasing or decreasing, but it stays the same. And then the total mechanical energy of block X remains constant when the block moves from point Q to point R. Now, because we have frictional force, which means we have losses to the system, the conservation, well, the mechanical energy of the block is not transferred from potential energy to what's this to kinetic energy, and there isn't even like a height change. The block isn't going up or down, but it's still on the same horizontal surface, but yet our velocity decreases, which means our kinetic energy decreases, but our potential energy stays the same. So that that is not going to have we're not going to have the same mechanical energy. So after all that me yapping, we can see that the only correct answer is B. Now to the main part of the question, question 2, where we have a crate P of mass 1.25 kilograms being connected to another crate of mass 2 kilograms by a light inextensible string. This means that the string does not compress, decompress, but it can be thought of as rigid, right? And it doesn't take any energy from the system. These are the assumptions that we make. The two crates are placed on a rough horizontal surface, meaning we have friction, a constant force F of magnitude 7.5 newtons acting at an angle of theta to the horizontal. Probably are going to be asked what is theta, and then is applied on the crate Q as shown in the diagram. The crates accelerate at that acceleration to the right, and this seems pretty simple. And this question starts from 2.1 and ends at 2.3.2. Right. Further analysis. There isn't really much. It's just to note that we are on a rough surface and we will have some force at an angle. So that would mean that we have components of this force, Fy and Fx. Alright, those are the components of this force. Now, with that being known, let us get into the questions. Now, for question 2.1, we are asked to state Newton's second law of motion in words. So I'm not really gonna write it, but you should know that the resultant force is directly proportional to the acceleration of the mass, while the same resultant force is inversely proportional to the mass of the thing that is being accelerated. Don't say the thing, but just know your definitions, and because you will be asked these definitions per question of this physics paper, every physics paper. Okay. So I guess I have to rewrite this whole thing. Apologies. So for crate P, we have a situation where we have our crate there, and because we are on Earth, we will have a force of gravity, which is the weight acting down perpendicularly. Doesn't look that way because I couldn't draw straight. And then we have a normal force, and because we have that string there, we are going to have some tension T, and then because there's movement or acceleration to the right, we're going to have a frictional force acting to the left. Alright, for question 2.3.1, we're asked to find the tension in the string, right? Now we're given most of the forces for crate P, right? So I would say let us work with crate P, where we have a situation where we have our F net being equal to mass times our acceleration, and this will take right as positive. We're going to have our tension minus our frictional force being equal to our mass multiplied by our acceleration, and we have values for our frictional force, our mass, and our acceleration, so let us substitute those. It's going to be minus 1.8, and that is going to be equal to 1.25, and that is multiplied to 0.1, and we shall see that our tension, after doing some mathematics, our tension is equal to 1.925 newtons, right? Let's not forget that this tension is applied to the right, and let us round it off to 1.93 newtons to the right. Alright, so for the last question of question 2, we have question 2.3.2, and as I predicted in the beginning bit of the question, we're asked to find the angle theta. Alright, so let us quickly do free body diagram of what's happening there by the block Q. Alright, so block Q is going to have tension from that block P. It's okay, let's just quickly do everything. We're going to have a normal force. Now we won't ask for this free body diagram, but I think it does help. We're going to have our weight, and then we have this force F applied at this angle theta. Alright, but this force F also has components to it. So we're going to have an X component, and we're going to have a Y component for our force F. Alright, now this angle theta is theta to the horizontal. Right, so we essentially have a triangle like this where the hypotenuse is F and the X component is Fx and the Y component is Fy. Theta is right there. Alright, now what would help us, I mean, we can compute all of these, but I think it's helpful to just do the forces in the X direction, right? So still, we're going to use our F net is equal to MA, where our right direction will be deemed as positive, and we shall see that our F applied in our cos theta direction, because we're doing the X, right? So we're doing our sum of forces in the X direction. F cos theta minus the tension, which is the only other force acting in the horizontal, is equal to our mass times acceleration, and we're going to have our force F being equal to 7.5 newtons as we were given, multiplied by cos theta minus the tension that we had in the beginning, which is 1.93, is equal to 2 multiplied by our acceleration 0.1, because this acceleration is applied to all of our masses in this question. We're going to have a situation where after some mathematics we're going to find that our theta is equal to 54.1, oops, that is not 19, apologies. Our theta is equal to 54.78 degrees, and that is our question.